Good afternoon, everyone. We are very grateful for giving us an opportunity to present a paper in IEEE International Conference on Computing, Power, and Communication Technologies, DUCON 2020. We are here to present a paper on a novel machine learning based wearable belt for fall detection. Our team members comprise of Kimar Desai, Preetham Mane, Manish De Silva, Parth Shingala, Amok Zare, and a faculty mentor, Sir Dayanand Ambavde. Our paper ID is 331. We are from Sardar Patel Institute of Technology. Problem definition. As mentioned in a report by United Nations Population Fund UNFPA, 6% of India's population is above 65 years. People above the age of 65 have a 25% chance of falling. One half to two-thirds of elderly falls occur in or around their homes. So we decided to come up with a belt to detect these falls. Introduction. These falls tend to damage hip, thigh bone, the pelvis, and may also cause spinal fractures. Owing to the necessity of elderly healthcare, a product that shall detect and mitigate the impact of a fall is required.
Objectives: to create a machine learning model to process the incoming real-time data to determine a fall or not, to detect a fall and alarm the dear ones before the user has completely fallen. System design. This image shows how our final product looks like. Our system consists of a waist belt on which all the components are mounted. The hardware components and their positions on the belt are as shown in the figure. The components used are as follows: a GSM module to contact dear ones as soon as a fall is detected, an Arduino Uno microcontroller to run our fall detection algorithm, MPU 6050 motion sensor, which consists of an accelerometer and gyroscope, and a battery to power all the components. The microcontroller and the motion sensor is placed towards the front of the belt. The battery and the GSM module are placed on either side of the belt. Methodology. The flowchart shown illustrates the working of our product. First, we read the values of accelerometer and gyroscope. After that, the sensor values are converted into a data point using a time window average technique within a duration of 0.5 seconds. This means that a single data point is obtained after averaging 0.5 seconds of data values to reduce false positives. This single data point has an 50% overlap of readings from the previous data point, which enables the system to capture the pattern in the sensor values. Further, the logistic regression model is run to classify this data point as a fall or non-fall. If the fall is detected, the GSM module is triggered and an alert message is sent to the family members. If no fall is detected, then the entire process is repeated again in a loop. This classification step executes every 0.25 seconds, which enables a system to detect fall within 0.25 seconds. Preparing the dataset. So now we would like to talk about the dataset that we created for the purpose of training our model. Our dataset consists of motion sensor readings for 5 daily routine activities. These activities were categorized as either fall or non-fall. The activities classified under non-fall are standing, walking, and jogging, whereas the activities classified under fall are sideward fall and backward fall. The accelerometer and gyroscope sensor values were recorded for a period of 2 minutes for all the above activities. These values were recorded when one of our team members was performing that particular activity and was wearing our proposed wearable belt. Standing. For standing, it is evident that both the plots are fairly constant. Walking. For walking, we can see small oscillation in the values in a periodic manner. Jogging. For jogging, the oscillation in the values is larger and in a periodic manner. Backward fall. For backward fall, a sudden dip and a rise is observed in accelerometer values, and a sudden rise is observed in the gyroscope values. Sideward fall. A similar pattern as backward fall is observed for sideward fall as well.
Machine learning. We will now see the machine learning model implemented by us. The dataset which we saw previously was split into train and test dataset. The machine learning model finally classifies a specific body action in every 0.25 seconds as fall or non-fall. Logistic regression model was implemented and tested on the dataset created. The estimation of regression coefficients was done, and this was finally implemented on controller. Model evaluation. As you can see in the figure, the green dots are the ones where the fall hasn't occurred, and the red dots are the ones where the fall has occurred. As you can see, the green dots are clustered at one place and the red dots are scattered all over. A sliding window of 0.5 seconds is implemented, where the mean of accelerometer and gyroscope readings was taken. The data is sequential in time, where each value depends on its past. Therefore, a single value cannot be a data point. A data point was calculated every 0.25 seconds, from which the machine learning model was trained. Result analysis. This is the classification report of our testing data. As you can see, the accuracy obtained is 100%, but the number of testing examples is very less. After this, real-time testing of the prototype was carried. We could then conclude a model could classify between fall and no fall in real time. Future scope. We will now see what are the additions which can make our current system even better. Our system is able to detect a fall before the user has completely fallen. This result can be leveraged to build a quick response safety airbag wearable system that can be used for protecting the user against a fall.
So these are the references for the research papers and articles that we referred.